All right, ladies and gentlemen, I'm back, and looks like my bandwidth is okay. I was having a few issues with the earlier class, but looks like it's good now. Better now, anyway. So, as I sent out an email earlier this morning, and it was a little bit lacking on details, but there were some technical issues on the Hayden McNeil website, so I extended the experiment to be due tonight at midnight rather than yesterday. I only discovered it yesterday and I didn't think about it, but yeah, so Hayden McNeil is open for another day. I know I've already sent an email out about the term exam, and we'll be discussing that sometime next week. So where we are at right now is looking, I guess, at the course material and continuing on with that. Last day, we started looking at buffers, and in looking at buffers, we ended up deriving the Henderson-Hasselbalch equation, and we'll be using that today and next few classes. But we also have this figure, which from a titration perspective is the region before the equivalence point. But what we were able to show was that the buffered range corresponds to the pH range of the pKa plus or minus 1. So at the half equivalence point, in the midpoint on this, where the base to acid ratio is 1, we have the pH is equal to the pKa. And then that region from 1 to 10 to 10 to 1, that's the ratios of base to acid, you have a plus or minus 1 around the pKa value. Last day we started some calculations, and we did this. We were able to calculate the pH when we added a tiny amount of hydrochloric acid to some amount of pure water. And I'll show you that in just a few seconds when we go over to the document camera, I guess tablet. We did this calculation where we created a buffer by mixing two solutions together, conjugate acid-base pair of formic acid and sodium formate. And not as a novelty, but to a new experience, we used moles in the ice table, and we're going to be doing more of that in the next couple of days as well. And the one thing we didn't get to do was to determine the pH when we added that same amount of acid now to the buffer. So let's go do that and follow our notes. So in the context of this was the calculation of the pH where, whoa, that was weird. Sorry. Where we added this to pure water and realized that pure water has a pH of 7. And adding a tiny amount of acid dropped that pH down to 1.19. It does look like the tablet is running a little slow, so I guess that means I will wait for the tablet. The next thing we did was that buffer. And in that buffer, we have, we did the entire thing in moles. It will catch up. And we had some of our initial conjugate acid-base pair. We added in X, or we calculated these values down below based on the concentration and volume. And we set up and we solved this entire ice table completely, not using the Henderson-Hasselbalch equation. We could have used the Henderson-Hasselbalch equation, but just to show you a new concept, here we worked in moles and we ended up with one final volume that needed to be done to convert to concentration quite literally on the fly when we calculate, plug it into the equilibrium constant expression. And what we were able to do here was show that the pH initial of this buffered solution is 4.14. What we need to do now is that last step, add some acid to this. And that is going to give us a neutralization process. So we have a neutralization reaction. That neutralization reaction takes our, since we're adding acid, our base, and we're adding acid to it to form formic acid plus, of course, our residual chloride. We're going to assume that the neutralization reaction goes to completion. This is like what we did when we were setting up ice tables. We assume it goes completely to the side favored by the equilibrium constant. Well, here we have an ice table, or sorry, a neutralization reaction that we're going to assume goes to completion. Then we'll deal with the products after this is done. Plugging in the values from that we calculated yesterday, we have 1.89 times 10 to the minus 2 moles of the formate, and 7.70 times 10 to the minus 3 moles of the formic acid. What we added was 6.5 times 10 to the minus 3 moles of hydrochloric acid. This is the benefit of moles in the ice table, is that the number of moles is never going to change. The concentration will change, but the number of moles will not. Since this reaction goes to completion, we have to figure out what the limiting reagent is, and just by inspection, it's fairly obvious that it is the hydrochloric acid. It's a smaller number, and stoichiometry is the same. So that, of course, goes down to 0 as it needs to for a reaction going to completion, and we're left with 1.24 times 10 to the minus 2 moles there, and 1.42 times 10 to the minus 2 moles there. Okay, so that's the first step. And we've added our acid, we've neutralized this. Now we have the next one being the equilibrium. Because formic acid is still weak, it will still reach equilibrium like this. And we have the Ka is 1.8 times 10 to the minus 4 moles per liter for this. That's a 4. There. So set up an ice table. And now we take the products from our previous one and we substitute them in. And, 1.42 times 10 to the minus 4, 1.24 times 10 to the minus 2. Or they're both times 10 to the minus 2. My apologies. And 0. And we're working in moles. Good. Because we have some of the conjugate acid-base pair, we have a buffer. And we can use the Henderson-Hasselbalch equation to solve this equilibrium, then determine the pH. And the pKa is 3.752 from our Ka value. And remember from last day, we showed that the mole ratio was the same as the concentration ratio. So this is the mole ratio of 1.24. The tablet's going much faster. I'm happier. And when we do this and plug the values in, we get a pH of 3.69. So the initial pH, just to remind you, was 4.14. That was the initial pH of the buffer. And adding acid dropped the pH to 3.69, which is a much smaller drop than going from 7 to 1.19. So to summarize what we have, that small amount of acid, 6.5 times 10 to the minus 3 moles, in the same volume of water, if it was pure water, it changed the pH by about a factor of 1,000,000. Whereas in the buffered solution, it changed the pH by about a factor of 2. That illustrates the nature of buffers. They resist changes in pH with the addition of acids or bases. That's the nature of a buffer. Are there any questions on that? I've noticed that my connectivity is poor, so I'm trying to close a few things to see if I can fix it. It's a little bit better. Okay. All right. Question. Yeah, well, I'm working on increasing my connectivity right now. File save, file close. Yeah, I'm working on it. Give me a second here. That might help it a little bit, I hope. Okay. The next example I want to look at is this one. Just let me know how the audio quality does. We have blood which is buffered at around a pH of 7.3. The buffering system is carbonic acid hydrogen carbonate. We have the ability to readily control the carbonic acid hydrogen carbonate buffer because we breathe, and we can control the amount of carbonic acid by regulating how much CO2 we retain in our bodies. So carbonic acid anhydrase, which converts carbonic acid to CO2 and water, can control how much carbonic acid we have in our bodies, and so it allows us to maintain a relatively constant pH in our blood, and that pH is 7.3. What I'm interested in here is the base to acid ratio at a pH of 7.3. So the buffered system that we have is this, and there is a Ka value of 4.4 times 10 to the minus 7 moles per liter for that. And what we want, the base to acid ratio at pH of 7.30. We have the Henderson-Hasselbalch equation. And this is what we want, that value right there. So I would like you to determine the pKa and then come back and work out what the base to acid ratio is for this system. Please go ahead and do that. and just type the response into the chat. Does anyone have a value for the base to acid ratio? That's not what I got. I didn't get 2.57. I got the same as Taylor, 8.78. But that suggests that we should probably work through this. So 7.30 is equal to, what is the pKa? Does anyone have that number? Just type it in. $6.357, yes. Okay, good. 6.357 plus log base over acid. And so that gives 0.943 is equal to log base over acid. And what we want to do is we want to take 10 to all of that. And 10 to all of that means that our base to acid ratio is equal to 8.78. Which is the number we have there. Good. Just remember, Haley, that it's negative log, so the Ka is 6.36. pKa is 6.36, not negative. All right, so we showed how that value was obtained, and so we can now go back and look at that base to acid ratio. In the context of the carbonic acid hydrogen carbonate buffer, that red dot shows you where this buffer is. Here what we see is that the blood is really capable at dealing with acids as they come into the body, but it's not very good at dealing with bases as bases are added to the body. Why might that be the case? Why has evolution given more protection from acids than bases? Anyone? We already talked about it in class, actually. Not today, but at the beginning of this unit. And Annika has that most foods are acidic. Yes, we talked about the acids that pervade our foods. Citric acid, ascorbic acid are common in the foods, the fruit that we eat. Bases are generally not in our foods. We find them toxic to us. So when an animal creates a poison, it very often is a base, and that dramatically affects our body. If you look at the profile that is right here for the hydrogen carbonate carbonic acid buffered system, our body can tolerate lots of acids. So even if we had hydrochloric, nitric, whatever acid, putting a small amount of acid on our body is going to cause the pH to go down. But we notice that because our nerves still function. Our nerves function and it itches or it hurts or it burns. And so we know that we've gotten in contact with an acid and we can go clean up. The problem is that when we add the same amount of base to our body, on our skin, we don't actually sense it because the pH increases very, very rapidly. And what ends up happening is that it denatures the nerve cells so they can't signal to the brain that, gee, there's something on your skin that's a problem, you should do something about it. So the base, which is actually more destructive in the first place because the pH changes dramatically, our body doesn't even have the ability to tell our brain this because the nerves have been denatured. So double whammy on the negative side of bases. In your notes, you had another example, but I think that example is actually in the problem set, so I'm not going to go through it here. I do want to jump to now look at acid-base indicators, and this is going to lead us into titrations. So acid-base indicators are nothing more than weak acids that happen to have different colors in their acidic versus basic forms. So I've given them the symbol IN or IND. And so the acidic form is in equilibrium with the basic form IN minus, and one or both of those are colored. The midpoint of that color change, where you have an equal amount of base to acid, is the pKa of the indicator. So here's just a selected range of indicators, and the pH is where they change color, and of course their color changes. And you'll note that, excuse me, we have indicators in a full list, indicators that change color at pretty much any pH range you want it to happen in. But also that some of those indicators are polyprotic. Cresol red and thymol blue change twice, and so does phenolphthalein down at the bottom of the list. I don't know, from a chemistry perspective, it's kind of really cool to take, like, say, thymol blue or bromophenol blue, the second and third ones on the list, and get to the point where you have yellow and blue. Right at the midpoint, there is actually a green transition right there. It does go green for a very small pH, at a very small pH range. So it's kind of cool. Phenolphthalein is a common indicator, and it is used in basic solutions because it changes pH at around pH of 9.2. It also changes back to clear at a pH of about 13.8. So if you're actually dealing with a very basic solution, phenolphthalein doesn't work as an indicator because it goes clear again. And just as a more of an interest sake, but also as an awareness that phenolphthalein isn't pink in all basic solutions. Really basic solutions, it goes back to being clear. This one slide details the titration process, and we're going to spend quite a bit of time looking at each of those 4 flasks at the bottom. To look at some of the terminology associated with titrations, we have A, that is the analyte, the entity that we're trying to analyze. What are we trying to analyze for? Yeah, that's our analyte. Our titrant is what we're using to determine the concentration of our analyte. And we also have an indicator here given the symbol IND. There are 2 relevant reactions. The first reaction, of course, is that of our analyte and our titrant. This reaction needs to be stoichiometric. It needs to be well understood And there generally can't be any other side reactions. So you have quantitative reaction of our analyte and our titrant to form some products. In addition, the titrant, usually the titrant, needs to react with the indicator to indicate that you've hit the, you used up all of the analyte. We'll get to the exact terms in a few seconds. So down here on the bottom left, we have our initial conditions. The one on the bottom left is our initial conditions, where you have your analyte and your indicator. This is literally the sample that you've taken an aliquot of, you've added a few drops of your indicator, and you're ready to go. Nothing else has been done to it. In the second flask, you are titrating with the titrant, and so the titrant is your limiting reagent in this process. So the analyte and titrant are reacting to form C, but you still have an excess of your analyte A, and nothing, of course, has happened to the indicator. I'll tell you what that one's called when you tell me, or after you tell me, what the third flask is called. What is the state we are in when we added a stoichiometric amount of analyte and titrant such that they completely cancel each other out, they've all reacted to produce C. Where are we in the titration in that third flask? Anyone? We're not at equilibrium, not at the endpoint. It's got a different name, but keep endpoint in the back of your head for another one. Excellent to the people. Equivalence point. The third flask is the equivalence point. It is where you've added a stoichiometric amount of analyte and titrant to produce product, but there isn't, you don't know you're at the equivalence point because there isn't an excess to trip the indicator. So I just want to go back to the first flask was your initial conditions. The second flask was before the equivalence point. The third flask is at the equivalence point. And when you add that extra fraction of a drop that reacts with the indicator to change color, that is called the what? Jada? The endpoint, yes. The endpoint is when you know you've used up all of your analyte and you've tripped your indicator. The goal in selecting an indicator is to make the indicator change color very, very close to the equivalence point so that the difference in volume is basically negligible. And then finally, the last flask is after the equivalence point. You have an excess of your titrant and it does whatever. So after the equivalence point. Those are the 5 states: initial conditions, before the equivalence point, at the equivalence point, the end point, and then after the equivalence point. All right. In the context of titrations, we have 4 possibilities. The analyte could be a strong acid or weak acid. It could be a strong base or a weak base. As chemists, we can't control the analyte. You get a sample that comes in, could be water, could be blood, could be, an unknown solution. You don't have the ability to control the analyte. So it could be strong or weak, acidic or basic. We do have the ability to control the titrant. And we pick the titrant to be a monoprotic, strong acid or base as required to titrate the analyte. Why monoprotic? It simplifies the nature of the calculations, and it also introduces the greatest pH change. And we'll see that in the titration curves in a little bit. And so in the titration curve, there are 4 unique regions. Those are the initial conditions, before the equivalence point, at the equivalence point, and after the equivalence point. We're making the assumption that we're going to see what happens with the indicator when we choose different indicators on the next slides. So those 4 regions are represented here. On the bottom left, the initial conditions. Just your analyte is present. Region 2, before the equivalence point, you're going through the titration, but your analyte is still in excess. Region 3, you're at the equivalence point. You've added a stoichiometric amount of analyte and titrant to your analyte, and all of it has been completely used up. And region 4 is after the equivalence point, where you have now an excess of your titrant. We'll come back to this picture in a little bit. I just want to go through how the pH is calculated at each one of these locations. What stops, Rafaro, I'll get to your question in a little bit, okay? Initial conditions. The pH is controlled by the analyte. That's all that's left. That's all that's in the flask, is only your analyte. If you have a strong analyte, it dissociates fully. If you have a weak analyte, it reaches equilibrium in solution. We've done both of those calculations already. Before the equivalence point, the pH is controlled by the excess analyte. If your excess analyte is strong, you have the excess analyte fully dissociating, and it's just a more dilute solution. And so you can calculate the concentration and therefore the pH. If you have a weak analyte, you now have a conjugate acid-base pair. You have a buffer. If you don't realize you have a buffer, you still have an equilibrium, and you can set it up and solve it using Ka as you normally would. So you can either use the Henderson-Hasselbalch or you can solve it using an ice table. It doesn't matter. As long as you realize you have some of the conjugate acid-base pair. So those are the calculations of pH initial conditions and before the equivalence point. At the equivalence point, the pH is controlled by the conjugate. So the analyte and titrant completely neutralize each other. They're both gone at the equivalence point. All you have left is C. That's all that's there. So if your analyte was originally strong, that means your conjugate doesn't have any basic or acidic properties. You have a neutral solution, and the pH is from water. pH is 7. If your analyte was weak, then the conjugate was also weak, and the pH is determined from the hydrolysis of the conjugate. And finally, after the equivalence point, the pH is controlled by the excess titrant. We get to control the titrant. It's going to be a strong acid or strong base, so it's always strong. And that excess titrant fully dissociates in whatever volume you've got, and you're able to calculate the pH from that. So after the equivalence point, it is always going to be either a strong acid or a strong base, because we get to control that. Rufaro, I know you've got a question. It's going to come up. It won't be immediately, but I'll be able to explain it in about 4 slides, where we'll see what happens when you pick the wrong indicator. So what's the difference between strong analyte and weak analyte titrations? So the initial pH of a weak analyte is dependent on the Ka-Kb, how much of it dissociates. So that is going to, the Ka-Kb value is going to determine what the initial pH is. The region between 1 and 2 is going to be linear for strong analytes and have some degree of curvature for weak analytes. It's a subtle point, but we'll see it when we look at the pictures. Region 2 is a buffer for weak analytes, titrations, and region 2 is independent of concentration. That's a unique factor. It's independent of concentration for weak analyte titrations, but it is dependent on concentration for strong analyte titrations. And there's pictures in your book that show what happens when you change the concentration of your initial weak analyte versus initial strong analyte and do the titration. For weak analyte titrations, pH at the half equivalence point is equal to the pKa. We looked at that with the Henderson-Hasselbalch equation. Halfway along, base to acid ratio is 1, pH equals pKa. For strong analyte titrations, the conjugates don't have any basic or acidic properties, so the pH is equal to 7. And for weak analyte titrations, the conjugate is also weak, and so it depends on the Ka value, but it will not be equal to 7. Does anyone have any questions on this? I'll get to your question in a second, Rufaro, but on this slide or what we've covered thus far. All right. So let's spend a little bit more time looking at what these titration curves look like, and then let's actually go about calculating one. This is the same slide as what you had before. It was a strong acid, strong base titration. You'll note that because the initial acid concentration is 0.1 mole per liter, the initial pH is 1 because it completely dissociates. So the initial pH is 1 under initial conditions. And the titration curve from regions 1 to 2 is basically a linear process. It doesn't change. At the equivalence point, point 3, the pH is 7 because the conjugate base doesn't have any basic properties, and so you get the pH determined only from the solution. You basically have a saltwater solution at the equivalence point and a neutral pH, pH 7. Here, an indicator was chosen that changes color, about 6.8 for bromothiamyl blues when it changes color, and so this would be a reasonable indicator to use. After the equivalence point, you just have strong base, and strong base reaches it's going to be limiting out at a pH of about 13, which is what you'd get from a 0.1 mole per liter strong base solution, strong base solution. The reverse, a strong base being titrated with a strong acid, is actually a mirror image of the previous one. So if this is a strong acid, the strong base titration now starts off at 13 and goes down. The pH at the equivalence point, since it's a strong base, strong acid titration, is still 7. Another indicator that would work fine here is phenol red, which is about 7.3, 7.4 as its pKa. And at the end, it becomes a strong acid, which is going to limit out to a pH of 1 as you add excess acid, 2.1 molar. Now let's look at a weak titration. Notice again, between 1 and 2, it's linear. Here there is a slight degree of curvature between regions 1 and 2. In here, the initial acid concentration, despite being 0.1 mole per liter weak acid, the initial pH isn't 1 because only a fraction of the acid dissociates. So the pH is something greater than 1, controlled by the Ka value. Region 2 is now a buffer, where the half equivalence volume has the pH equaling the pKa, and you have a buffered region in this at this point. So there's a buffered region that's created. Region 3 is the equivalence point, and now everything has been converted to the conjugate. And so if HA is weak, A minus is also weak. And so A minus is going to hydrolyze in solution and give you a slightly basic solution. And in this case, the calculated pH is around 8.8, or sorry, 8.4. Rufaro, this is what comes into your question. I've shown two indicators here just for to illustrative purposes. Phenolphthalein, which changes pH at around 9, would be a reasonable indicator because it's a very steep transition here. So a fraction of a drop is going to take it from a pH of 7 to a pH of about 11. So phenolphthalein works just fine. However, this blue and red one, which is resorcin blue, won't work. It's going to take a lot of volume of the base to cause this solution to change from blue to red. It would be a bad indicator because the indicator changes color before you actually hit the equivalence point. We can see this again when we do a weak base with a strong acid titration. Okay, again, the initial pH isn't 13. It's something less than 13 because it's only partially dissociated. Region 2 is a buffered region. Again, at the half equivalence point, the pH equals the pKa. Region 3 is the equivalence point. And now, because the conjugate acid is weak, you have a slightly acidic solution. And here, resorcin blue would be a great indicator for this, but phenolphthalein would not. As illustrated here, phenolphthalein to change from pink to clear would take a large volume, but resorcin blue would take only a fraction of a drop to go from pH 7 to pH 3. And after this, you have an excess strong acid, and that's just excess diluted in the volume. Rafaro, does that answer your question? Good, excellent. This next slide puts all of them together so you can see the similarities and differences. Strong acid titrations are on the left-hand side, and they are literally mirror images from each other, with a pH of 7 being the equivalence point. Also notice on the strong titration that the length of the vertical transition is quite large. It from about a pH of 3 to a pH of 10 is the range of this vertical transition. A fraction of a drop is going to take you from 10 to 3 or 3 to 10. If you look at the weak titration, the length of the vertical transition is much shorter. It's only about 3 or 4 pH units, 6 to 10 or 6 to 11. And they're still mirror images of each other. It's just that you have a little bit more information. You have your buffered region in both. At the half equivalence point, the pH equals the pKa. In the weak acid titration, the equivalence point is basic because the conjugate is a weak base. And in the one below, in the weak base titration, the weak acid is all you have left at the equivalence point. And because it is a weak acid, you'll have a slightly acidic solution. Does anyone have any questions on this? All right. Last thing I want to look at is that of a polyprotic acid titration to show you that it's not the easiest thing to work with. The vertical height between the 2 points for each of these equivalence volumes is very small, and it is not sharp. It's actually gradual, not steep. So using indicators for a polyprotic acid or base is actually quite difficult to do. Something like this should best be titrated using a pH meter or the like. But the other factors are still the same. You have an initial pH that's controlled by H2A, and we did a calculation, and we actually even showed that HA minus was negligible. We can calculate the pH of A2 minus because it hydrolyzes in solution, and we could even show that HA minus contributes negligibly to the pH if you start with a solution of A2 minus. At the half equivalence volumes for both Ka, the first equivalence point and the second equivalence point, pH equals pKa1, pH equals pKa2. The only pH on here where we can't actually calculate is the solution of HA minus, and we looked at that the other day because HA minus is amphiprotic. That is, it acts as both an acid and a base, and we don't work with multiple equilibrium systems with an ice table. It can't be done. However, we can actually estimate the pH of HA minus because it's halfway between pKa1 and pKa2. So if we actually just take the midpoint between pKa1 and pKa2, we get a fairly good estimate of the pH at the first equivalence volume. It's a workaround, but I'm expecting you to do it. So, in terms of calculating a titration curve, all of the points there, it's going to be done as a two-step process. The first step is going to be the neutralization. We have an acid and a base. We're going to assume that the neutralization precedes the completion. Then the second step is to look at what you have left over, whatever excess reagents there are, and how do they contribute to the pH? They are going to establish the pH. Since the volume is changing, it is much more convenient to actually work in moles because the number of moles doesn't change, but the concentration is always going to change. And that leads us to the example. This is the example that's going to take us today and tomorrow to complete. And I have the ability to do part A here. Right. So this is multi-step just to look at a lot of different aspects. But what we have here is that concentrated HF overflow, spilt over and came into an overflow container. It's positive that they're using an overflow container. You titrated a 10 ml sample of that with sodium hydroxide, and you found out what the equivalence volume of sodium hydroxide required to reach the equivalence point is. And we're going to today determine the hydrofluoric acid concentration in the overflow container, and then determine the volume of concentrated hydrofluoric acid that was spilt for the fun of it, and determine the pH after the addition of varying amounts of sodium hydroxide, and then graph that titration curve. So the first thing we're going to do is determine the hydrofluoric acid concentration in this. And just to remind you of the chemistry, we have HF is reacting with sodium hydroxide to give sodium fluoride plus water. That is the neutralization reaction. We really don't care about the sodium too much, so we can simplify this to give you this reaction. It will come back, I hope. And so this is the neutralization reaction that we are going to be working with later, but I wanted to put it here. To calculate the HF concentration in the overflow container, we take our titration data, 0.01863 liters of sodium hydroxide. Concentration to give you moles of sodium hydroxide, 0.0572 moles of NaOH per volume of NaOH. The chemical reaction also gives us the stoichiometry, and it is 1 mole HF over 1 mole NaOH. I'm very careful about what cancels. Moles of sodium hydroxide cancel with moles of sodium hydroxide, similarly with volume. And now we have 1.066 times 10 to the minus 3 moles of HF. This was in a volume of 10 mils. That was the aliquot that was taken and titrated. And so the concentration is 0.1066 moles per liter of HF. And we're carrying an extra digit through for our calculations. So that is the concentration of the, hydrofluoric acid solution in the overflow container. And I'm slightly over time. Thank you very much for your patience. If you have any questions, I will gladly hang around and can answer your questions for you. So otherwise, have a great weekend, and I'll see everybody on Monday.